It has been the dream of many people for the eventual colonization and settlement of space, going as far as devising detailed plans for such endeavors. While beyond the capabilities of today's space programs and private space ventures, it is anticipated that space technology will evolve and advance to enable those dreams to someday become reality. Many of those plans entail the exploration and colonization of Earth's moon, Mars, and the other bodies in the solar system, and those scenarios are a well-known trope in science fiction. Beyond merely settling and living on the moon or on other planets, some even envision whole cities and industrial operations being developed as colonization expands further. However, there are even those who advocate living in space rather than on the surface of a moon or planet, building upon the concept of space stations. Space stations are both a major part of many science fiction stories and have been a major aspect of real-life space exploration dating back to the earlier years of space exploration up to the present day, with the series of Soviet Soyuz space stations during the 1970s and early 80s, as well as the U.S. Skylab space station in 1973. These were followed by the Soviet, later Russian, Mir space station in 1986, which was operational until 1999, and culminating with the current International Space Station, which has been in orbit and operational since 1998. More recently, China's space program has embarked on the construction of the Tiangong space station. Additionally, there are now private space companies developing their own space station designs, with plans for them to be built and operational in the near future. Inspired by the promise of a future in space, during the mid-1970s, there were serious studies conducted on the possibility of space station concepts far larger and far more ambitious than past, present, and even future space station projects. The studies resulted in the designs for massive space habitats that would essentially be cities in space and would serve as space colonies inhabited by thousands of people. During the summer of 1975, NASA and Stanford University held a 10-week conference, later known as the Summer Study. During this conference, plans for space colonization were discussed in detail, leading to studies of possible habitat designs. The studies expanded on previous studies on space colonization by Princeton University professor Gerard K. O'Neill, who served as the technical director of the study. The design studies were an extension of an earlier feasibility study conducted in 1969 by O'Neill and students at Princeton University. Aspects of a space colony that were explored in the study included the use of solar energy to sustain the closed ecosystem such a colony would require, along with space manufacturing. Materials to build the colony would be made from lunar material mined at a lunar colony and sent into space by a mass driver, which is a sort of electromagnetic railway that would accelerate a payload to lunar escape velocity to be sent to the colony site. The colony would be located at the Earth-Moon L5 Lagrange point. The Earth-Moon L5 Lagrange point, a stable point trailing the Moon, would keep the habitat in a relatively fixed position in the Moon's orbit around the Earth. Lagrange points are points in space where the gravity between two bodies is balanced. The L5 Lagrange point was chosen due to the stability of a colony at that location, which would remain relatively in place but slowly orbiting the exact point over the course of a month. This would allow for multiple colonies to be placed at the same point. 3 designs were proposed and studied, the first one being referred to as the Bernal Sphere. This was a design for a spherical space habitat initially proposed in 1929 by John Desmond Bernal. Bernal's design was for a hollow, non-rotating spherical structure 10 miles in diameter, inhabited by 20,000 to 30,000 people. A variation of Bernal's original design was proposed by O'Neill and was called Island 1, which was to be a sphere about 1,600 feet in diameter. The colony would rotate at just under 2 revolutions per minute to create centrifugal force to produce artificial Earth-like gravity at the sphere's equator. The interior landscape would be like that of a large valley running all the way around the equator of the sphere. Inhabitants' homes would be built around the interior surface of the sphere. Agriculture would be done in separate greenhouse-like modules. Sunlight would be directed by external mirrors to large windows near the poles of the sphere. The spherical shape was chosen for its ability to hold air pressure and mass efficiency at providing radiation shielding. O'Neill also proposed a larger design called Island 2 that would be slightly over a mile in diameter with a circumference at the equator of 4 miles. This version of the colony would be a habitat for 10,000 people, serving as the residential area of a space industrial facility. A variety of space-based industries were envisioned, including the production of materials for the construction of other space structures. As with the Island 1 design, inhabitants' homes would be built around the inner surface of the sphere. Artificial gravity would be about 1g, or like that of Earth's at the equator, gradually lessening as one moved towards either pole. This would allow for some interesting possibilities for lower zero-gravity recreational activities, such as zero-g sports and human-powered flight. Along the equator would be a small river, with riverbanks comprised of soil imported from the moon. Distances inside the colony would be short enough that people would be able to walk or bicycle around the interior. Structures at each pole of the sphere would be for docking of spacecraft, as well as the location of the habitat's zero-g industrial activities. Large radiators to carry excess heat away into space would also be at these locations. Closer to the sphere, greenhouse-like areas would be located for the habitat's agriculture to be carried out. Mirrors arrayed around the equator of the sphere would reflect sunlight to mirrors near each pole, which would in turn reflect the sunlight into the interior of the sphere, giving the inhabitants natural sunlight. The mirrors would be adjusted to simulate a day and night cycle. At the time of the design studies, it was hoped that such a space colony would be built and inhabited by the early 1990s, with the anticipated infrastructure and industrial capabilities in place to allow for the construction of the colony. In addition to industry operating on a colony producing satellites to be sent to lower Earth orbits and producing other spacecraft, once the colony is fully operational, one major industrial process that could be carried out would be the production of materials for the building of new colonies. These later colonies would also be located at the L5 point along with the original colony, further advancing the colonization of space. The second design is known as the Stanford Torus. The resulting design was an immense structure resembling a bicycle wheel, hence the term torus being applied. It was to be large enough to be populated by 10,000 people, more akin to a small community. Like the Bernal Sphere, it would be positioned at the Earth-Moon L5 Lagrange point. The habitat would be a tube, 427 feet in diameter in the shape of a wheel, slightly over a mile in diameter, and about 3.5 miles in circumference. People would live in the ring, with the ring connected via 6 large access tubes, like spokes, to a central hub, which would serve as the docking location for spacecraft. The spokes would be 48 feet in diameter and would allow for entry and exit to the living and agricultural sections in the ring. The habitat would rotate at 1 revolution per minute to simulate Earth gravity via centrifugal force. The interior would be illuminated with natural sunlight by a large stationary mirror positioned directly above the hub. The mirror would be inclined at a 45-degree angle to the habitat to direct sunlight onto a series of smaller mirrors that would then reflect the sunlight into the habitat's interior via a series of louvered mirrors that would allow light into the colony but also acting to block cosmic radiation. A large paddle-like structure beneath the hub would serve as the radiator carrying waste heat into space away from the colony. Even the possible use of a magnetic field in addition to the shielding of the structure itself as radiation protection was discussed in the study. Artificial gravity, despite the additional complexity of a rotating habitat, would be required to simulate an Earth-like environment and to avoid long-term problems among the colonists that would be caused by living in zero-G. The interior of the ring would be akin to a long glacial valley on Earth, with the ends curving upward and meeting overhead to form a complete circle. The interior space would be large enough to allow for flexibility of design and a variety of views and scenery within the colony, including allowing for individuals to design their own living space. It would be divided into 3 residential areas with 3 agricultural areas between them. This would minimize the feeling of living in an artificial environment. The colony interior would also be designed large enough for areas including residential areas, commercial shops and offices, public areas, light industry, open spaces such as parks, and transportation, along with areas for subsystems such as electrical transformers and power lines, and water treatment. Population density would be like that of a small suburb. The large amount of sunlight available to the colonists would allow them to raise enough food for themselves on only 156 acres inside the agricultural areas of the ring. The abundance of sunlight available to the colony would also allow for processing of ore from the moon that would be sent to the colony from a lunar base. Industrial operations would entail the use of solar furnaces to refine metals and other materials from lunar material. Zero-gravity material processing would be carried out in the hub of the colony, since being at the center negates the artificial gravity of the ring section. The habitat would need 10 million tons of mass, with materials being extracted from the moon or from mining asteroids. As with the Bernal Sphere, materials from the moon would be launched to a mass catcher at the L2 Lagrange point and moved to the L5 point for processing by the colony's industrial facility into construction materials. Construction of the colony would begin with the assembly of the hub section, then the spokes, and then the ring itself. Once the ring had been completed, the rotation would be started to facilitate more construction workers and colonists arriving to begin their work building the interior spaces. The goal would be to have people living permanently in space, working and raising families as they would on Earth. The third and most ambitious and largest of those designs proposed was O'Neill's Island 3 design, better known as the O'Neill cylinder. The cylinder colonies would be massive structures, dwarfing the other designs, and envisioned to be 5 miles in diameter and 20 miles long. Like the Bernal Sphere and the Stanford Torus, this would also be constructed from materials mined on the moon by a lunar base and sent to the colony's location by a mass driver. As capabilities advance further, colonies would be built from materials mined from asteroids. Also, like the other 2 designs, it would be located at the Earth-Moon L5 Lagrange point. In each cylinder, there would be 6 equal-sized sections running the length of the structure. 3 would be windows, the other 3 being inhabited land sections. The cylinders would be in pairs and connected by cables and would rotate in opposite directions to remain aimed at the sun. The rotation rate would be 28 times an hour to create Earth-like gravity. The central axis would be a zero-G region with facilities for zero-G recreation activities located there. People would live along the interior surface of the sphere. In each cylinder, large mirrors hinged at one end of the window sections would be angled to reflect sunlight into the cylinders. Day and night would be simulated by adjusting the position of the mirrors, opening the view from the windows to space. Movement of the mirrors would also give the illusion of the sun moving and creating natural sun angles during the simulated day. A 20-mile diameter outer agricultural ring rotating at a different speed would be where the colony's farming would be carried out. The colony's industrial sections would be at the center of each cylinder, facilitating manufacturing processes that would benefit from being conducted in zero-G. O'Neill believed that living aboard such a colony would be better than living in some places on Earth due to the abundance of food, climate and weather control, and the absence of pollution. Activities among the inhabitants of the colony would include Earth sports and other activities due to the very large interior space of the colony. The scale of the colony would be truly massive, with the interior space large enough to have hills, lakes, and even space for large terrestrial structures such as a large suspension bridge, as well as buildings. Even clouds would be able to form inside the colony. The land area inside would be 500 square miles with space for several million people, or equivalent to the population of some of the largest cities on Earth. This would mean that multiple colonies such as this could have tens of millions of people living in space, alleviating overpopulation on Earth, along with moving industry into space to mitigate the environmental effects of pollution. As with the other colony design proposals, while some involved with the study assumed the colony would be built and inhabited by the early years of the 21st century, as previously stated, it has turned out to be extremely ambitious and beyond the capabilities of current space programs or private space ventures, even more so for something on the scale of an O'Neill cylinder. However, even this is one thing that might have been that still has promise for the future once spaceflight capabilities and technology have advanced enough to allow such a massive project to be carried out. Perhaps after examples of the smaller colonies are built and inhabited, and in this case, science fiction would become reality, and humanity would truly become a spacefaring civilization. Thanks for watching, and if you've enjoyed this, please check out the other videos on this channel and click like and subscribe. And remember, when the future was cool.